Ever look at a really tricky problem and just wonder if there's a more elegant way, like an efficient way to actually solve it? Today, we're taking a deep dive right into the heart of dynamic programming, DP. Specifically, we want to nail down those core characteristics, the ones that are kind of like a secret handshake telling you if DP is, well, the right tool for the job. We're pulling insights from some great material, especially a really detailed look at DP characteristics from Hello Algo. So our mission today is to give you a really lasting understanding of these fundamental properties, optimal substructure and statelessness. These are what make DP so powerful for certain problems. Think of this deep dive as helping you build a new lens, sharp and clear, for spotting those complex challenges you can actually solve efficiently. This is for you to build that intuition.
Absolutely. And to really get what DP does, it helps to see where it fits, algorithmically speaking. You often hear dynamic programming mentioned alongside things like divide and conquer or maybe backtracking. And they do share a theme, right? Breaking big problems into smaller ones. But here's the key difference, the really crucial part. Divide and conquer usually deals with subproblems that are totally independent. Dynamic programming, on the other hand, it shines when those subproblems are interdependent, and this is important when the same subproblems keep popping up, overlapping subproblems. DP is also really, really good for optimization problems, finding minimum costs, maximum profits, shortest paths, that kind of thing. Now, having overlapping subproblems is necessary, but it's not quite enough on its own. There are two more characteristics that really enable DP. These are the properties that let it turn a potentially massive exponential problem into something much more manageable, usually polynomial time. And those are optimal substructure and statelessness.
Okay, let's unpack that first one then. Optimal substructure. The name itself sounds, well, a bit formal. People often say it's about building the best solution from the best smaller solutions. But what does that actually look like? How does it work in a real problem?
Well, that simple phrase is actually pretty spot on. Optimal substructure means exactly that. The optimal solution to your main big problem can be constructed just by combining the optimal solutions you've already found for its subproblems. So if you figured out the best way to solve all the little pieces, then those best results automatically combine to give you the best result for the whole thing. It's a guarantee, really. Powerful stuff.
Where the source gives a classic example, which really helps make this concrete, the minimum cost of climbing stairs problem. So imagine you've got this staircase, right? Each step has a cost to land on it. You start at the bottom, let's say step 0, maybe 0 cost. You can jump 1 step or 2 steps at a time. And the goal is simple. Reach the very top step with the absolute minimum total cost.
Exactly. So for this kind of problem, we define our DP state. Let's say DPI. DPI represents the minimum cumulative cost to reach the ith step. So dpi itself is the optimal solution to the subproblem. What's the cheapest way to get to step I? Now think about how you could have arrived at step I. You absolutely must have come from either step I1,
A one-step jump,
or step I2.
the two-step jump.
Right. So the minimum cost to actually reach step I has to come from taking the minimum of the cost to reach those preceding steps.
So the minimum of dpi1 and dpi2.
Precisely. And then you just add the cost of landing on step I itself. And that leads us right to the state transition equation, which the source gives as dpi equals mine, dpi1, dpi2, plus cost of.
And that equation right there, that's where you see optimal substructure perfectly laid out. To find the optimal cost to step I, the dpi, you're explicitly using the optimal costs you already figured out for the subproblems getting to I1 and I2, the dpi1 and dpi2. You're taking the guaranteed best ways to get to those earlier steps and using those best to find the guaranteed best way to get to this current step. It's optimal building on optimal. It just clicks.
Exactly, it clicks. Now, of course, to make this work, you need a starting point, base cases. So for this problem, the minimum cost to reach step 1, dp1, is probably just the cost of step 1, cost 1, assuming you start before step 1. And dp2, well, that depends on the costs of step 1 and 2 and how you got there from the start. You figure out these initial dp values, and then you use that transition equation, dpi is mine, dp1 and dpi2 plus cost d, to build up the rest. Step 3, step 4, all the way up to the top step you're aiming for. And something the source points out, which is pretty neat, is that sometimes DP lets you optimize space too. For this specific problem, notice how calculating dpi only needs the results from dpi1 and dpi2.
Right. You don't need dpi or anything earlier.
Exactly. You don't need the whole history, which means instead of storing a whole array of DP values, ON, memory, you can actually get away with just keeping track of the last 2 values. That brings memory down to constant O1. Yeah, it just shows how understanding the structure can lead to these nice efficiency wins.
The source also mentioned something interesting. about the interpretation of optimal substructure being kind of flexible. They contrasted this minimum cost problem and optimization goal with the simpler version where you're just counting the number of ways to reach the top.
Yeah, that's a really good point they make. In the counting version, the transition is usually something like d pi by equals d pi 1 plus d pi 2. You're adding up the ways. The goal isn't minimum or maximum, it's a total count.
Right.
But the underlying structure still holds. The total ways to reach step I is built directly from the total ways to reach I1 and the total ways to reach I2. You could even stretch it and say the maximum number of ways to reach it is built from the sum. I mean, the principle holds if the goal changes. The source essentially says that the definition of optimal just adapts to what the problem asks for. Minimum cost, maximum profit, total count. The core property is about whether you can combine the best results from subproblems, whatever best means, for that specific problem to get the overall best result.
Ah, okay. So it's less about the specific function like min or max,
Exactly.
and more about whether the problem solution has this compositional structure.
Yeah.
That makes sense. Fascinating. All right, let's shift gears. The second crucial characteristic, statelessness. What exactly does it mean when we say the path you took doesn't matter for where you can go next? Sounds a bit zen.
Huh. Well, maybe a little. In the DP world, statelessness means that if you're in a specific state, let's stick with the stairs, say you're on step I, the valid next steps you can take. They depend only on the fact that you are currently at state I.
Sure.
They are completely independent of the whole sequence of jumps you took before that to arrive at I. The history before this moment is irrelevant to the possibilities from this moment.
Okay.
Think about the very simplest stair problem again. No cost, just jump 1 or 2 steps. You're on step I. Your options are I plus 1 or I plus 2. Does it matter at all if you got I from I1 or from I2?
No, not for where you can go next. The options from I are always the same.
Right. That problem has simple statelessness. The stata tells you everything you need to know about the future transitions.
But then the source throws that curveball you mentioned.
Yes.
Stair climbing with constraints.
Right.
The rule is you cannot jump one step twice in a row.
Yes. And this is where that simple idea of statelessness breaks down. If you're standing on step I, you actually can't decide your next valid move just based on being at I.
Why not?
Because you absolutely have to know how you landed on step I. If your last jump, the one into step I with a 1-step jump from I1, then the constraint kicks in. Your next jump must be 2 steps to I plus 2. You can't jump 1 step again.
Ah, right.
But if your last jump into step I was a 2-step jump from I2, then you're fine. You can jump 1 step to I plus 1 or 2 steps to I plus 2 next. So the immediate past that very last jump becomes critical information. Simple statelessness, based just on position I, is gone. Violated.
So DP just fails here.
Not necessarily. This is where DP gets clever. The solution, like the source explains, is to redefine what we mean by state. We expand the state definition to include that necessary bit of history. Instead of just DP meaning, say, the number of ways to reach step I, we use a 2D state, DPI, J. This means the number of ways to reach the ith step, and D, the last jump taken to get there, was J steps long, where J is either 1 or 2.
Okay, so the state now includes the position and the last action.
Exactly. That expanded state I, J effectively packages the critical piece of history into the definition of the state itself. And now, with this richer state, we can write new state transition equations that work with the constraint. Let's think about how. To reach state I, 1, that means you're on step I, and your last jump was 1 step. Where must you have come from?
Step I1.
Right. And what must the jump into step I1 have been?
Because you can't have 2 one-step jumps in a row.
Yeah.
The jump into I1 must have been 2 steps.
Precisely. So the number of ways to arrive at I1 must be equal to the number of ways you could arrive at state I1 too. That gives us DP1, one exempli 1 Purdue.
Okay, that makes sense. What about landing with a 2-step jump?
So to reach state I2 on step I, last jump was 2 steps. You must have come from step I2. Now, is there any constraint on the jump that landed you on I2?
No, because the current jump is 2 steps. It doesn't matter what the previous one was.
Correct. So you could have reached step I2 via a 1-step jump, state I2-1, or via a 2-step jump, state I2-2. So the total number of ways to reach I2 is the sum of the ways to reach I2-1 and the ways to reach I2-2. That's DP1-2 equals DP1-1 plus DP1-2.
Got it.
And again, you'd need initial states for this 2D table. Like for step 1, the only way is a 1-step jump from the ground, so maybe DP1-1 and DP1-2 equals 0. For step 2, you could only land there with a 2-step jump from the ground, assuming the rule applies from the very start. So maybe DP2-1 and DP2-2 was 1. The exact base cases depend on the precise problem setup, but you define them for the start.
Okay, wow. That's actually quite clever. So the trick is, by expanding the state to IJ, You've packaged the necessary history, what the last jump was, right into the current state definition. And from that new, more detailed state, the future is independent of the history before you reach that specific IJ state.
You got it.
You've basically restored the property DP needs just by being smarter about defining what being in a state actually means for this particular problem.
Exactly. It shows statelessness isn't always simple or obvious. Sometimes the state you need to track is more complex than just a single number or position.
Okay, so we can handle some history by beefing up the state definition. But what happens when the history gets really complicated, like when past actions have these cascading long-term effects that change the whole landscape of the problem in, well, unpredictable ways?
Yeah, that's where standard DP approaches often hit a wall. The source brings up another stair example for this: stair climbing with obstacle generation. Sounds ominous.
It does. What's the rule?
The rule is, whenever you climb to step I, an obstacle is instantly placed on step 2I, and you can never land on an obstacle.
Oh, wow. Okay, so every step I take potentially blocks a future step.
Exactly. The challenge here is huge for DP. Every single step you take creates a new, permanent constraint somewhere else on the path, 2I. So the set of available steps for all future jumps is constantly changing, and it changes based on the entire sequence of steps you've taken so far.
Not just the last step, or the current position.
Nope. The possibilities from step I don't just depend on being at I, or even the IJ state we discussed. They depend on the sum total of all your previous steps, because each one might have blocked off a future option way down the line. This problem has, as the source puts it really well, very serious state effects. The state is deeply affected by history.
So what happens to DP then?
Well, for problems like this, where the future is so deeply tangled with the whole complex history, trying to define a DP state that captures all that necessary past information, it becomes practically impossible. Or, if you could define it, the state space would just explode. It would become enormous, and DP wouldn't be efficient anymore. It might take exponential time again. Remember, standard DP relies on the future being predictable from the current state definition. When that state itself needs to somehow encode too much complex path-dependent history, DP struggles. Problems like the classic traveling salesman problem, TSP, they share this kind of characteristic. The best path forward, the available options, the costs, they all depend heavily on the specific sequence of cities you've already visited. So for these really complex combinatorial problems, you often have to turn to other kinds of algorithms, things like heuristic searches, maybe genetic algorithms, sometimes reinforcement learning. These approaches aim to find good, practical solutions, even if they can't always guarantee finding the absolute perfect optimal one in a reasonable amount of time like DP can for the problems it fits well.
Right. Okay, so let's try and wrap this up for you listening. Let's recap the core ideas. Dynamic programming is clearly a super powerful technique, especially for those optimization problems where you see the same subproblems showing up again and again, overlapping subproblems. But its real magic, its efficiency, gets unlocked when the problem also has these two crucial characteristics we've been digging into.
That's right. First, you need optimal substructure. That's the ability to build the absolute best solution for the whole problem just by combining the absolute best solutions you found for its smaller parts. And second, you need statelessness, which means the possibilities for future steps, the transitions from any given state, they depend only on that current state, not on the full historical path that led you there.
And we saw that even if simple statelessness seems broken, like needing to know the last step taken, you can often rescue the DP approach by making your state definition richer, by effectively bundling that necessary piece of history right into the current state, like with DPI. But then there are problems with really deep, complex, unpredictable historical dependencies, like that obstacle generation example. And for those, standard DP often runs into trouble because defining a manageable state becomes, well, intractable. Exactly. And recognizing these two characteristics, optimal substructure and statelessness, or maybe how you could achieve statelessness with a clever state definition, that's really the key. It helps you identify when dynamic programming isn't just, possible, but when it's likely the most elegant and efficient tool you have in your algorithmic toolbox. It fundamentally changes how you look at certain kinds of problems.
This has been a really insightful deep dive into these foundational properties of DP. We really hope unpacking optimal substructure and statelessness this way has given you a clearer picture, maybe something that'll stick with you as you tackle new challenges, whether in coding or elsewhere. Thanks so much for joining us. Yeah, thanks for listening. And maybe just a final thought to chew on. As you look at any system or problem, could be a programming puzzle, could be something totally unrelated in the real world, try asking yourself this question. Can the best overall outcome here be built purely from the best outcomes of the smaller pieces? Does the future from this point truly depend only on where things are right now, or does the entire, maybe messy path taken to get here fundamentally change what's possible next? Spotting those patterns, that's really about spotting the potential and maybe the inherent limits of powerful structured approaches like dynamic programming. Food for thought.